In this video, I will show you how to apply the Biot-Savart's law for a linear line current distribution. So what I have here, I have written Biot-Savart's law for a short wire with a current, and the small magnetic field that short current carrying wire is making is equal to mu naught over 4 pi the conventional current times delta L, which depends on the direction of the conventional current and also on the length of the wire, cross product with r hat divided by the magnitude of r squared. And I want to remind you, in this expression, the vector r is r observation minus r source, the position vector of the observation location minus the position vector of the source location. Now, the current carrying wire that I have here is a straight line. The entire length is L, and I have placed the origin of the coordinate system at the center of this wire. Positive x is to the right, positive y points up. And because of this convention, the positive z direction, and I will indicate that, goes out of the board. So this is the positive z direction. Now, the observation location is, let's say, somewhere here. Okay, it is on the x-axis. So that means I will need to write r obs is equal to x 0, 0. Now, the process that I will use is similar to the one that we used for finding electric fields. I have to divide the current distribution into small pieces. In this case, I need to divide the wire into short current carrying wires. And I need to assume that all of the current of each short wire is essentially can be modeled as a current that is located exactly at the center of that piece. Let me give you an example. So for example, and also the piece that you choose will have to be an arbitrary piece. So let's say I'm choosing this one. Okay, this is a short piece of wire. It has a length of delta y, and to find the magnetic field that this short piece of wire creates at the observation location, I can use this form of Biot-Savart's law. Now, once I do this, then I will need, as we did in electrostatics, I will need to add up the contributions to the magnetic field from all short pieces of wire. And then once I have that sum, I will need to move on and convert the sum into an integral by taking the limit where the length of each short piece of wire goes to 0. And this will give me the analytical expression for the magnetic field. Now, I have written the observation, the position vector of the observation location, and I also need to write the position vector for the source. Since my wire is aligned with the y-axis, I will have 0, y, 0. And then this means the vector r, using r obs minus r source, I will have x minus y and 0. This will give me a magnitude of r, the square root of x squared plus y squared, and then the vector r hat, the unit vector, this is r over the magnitude. So this will be x divided by the square root of x squared plus y squared, comma, minus y divided by the square root of the same quantity, x squared plus y squared, comma 0. Now that I have the vector r hat, I need to move on and calculate the cross product. But before I do that, I will need to write the vector delta L. Okay, delta L points in the direction of the conventional current. Let's make a choice. Let's say that the conventional current flows in the positive y direction. So this is I, and this means delta L will be my delta y times y hat. Okay, I'm using delta y because this is the length of the short piece of wire that I'm using. Okay, I'm finding the magnetic field that this small piece of current is creating at the observation location. That's why I have delta L equals delta y times y hat. The conventional current points in the positive y direction. Now I need to find the cross product between those two. So my next step will be to do delta L cross r hat. Now the vector delta L points in the positive y direction. The vector r hat, okay, the vector r goes from the source to the observation. Now there are several ways that you can use to find the cross product, one of which is using the determinant. And if you are comfortable with determinants, go ahead and use that. If not, you can find the expression for the cross product written as a determinant, and then you can also find the expression that allows you to simplify that determinant and directly plug in the numbers. And I can show you, I can show you how to calculate that cross product, but I will do that here. So we got the vector delta L is a vector that points in the y direction, and if I remember correctly, the r hat was x over the square root comma 0. Now what we wanted to find is delta L cross r hat, and I can show you what's that determinant, what the determinant looks like. You got on the first row x hat, I'm gonna use some space, y hat, z hat. Now the second row will have the xyz components of the first vector of the cross product, and that will be the delta L. So that will be a 0, delta y, and 0. And then I need the xyz components of the second vector of the cross product. So that will be x divided by the square root of x squared plus y squared, and then minus y over the square root plus x squared plus y squared, and then I have a 0. Now I will show you how to do the first term, and I will let you do the rest. So when I find, that's the way that I remember it, when I find the x hat component, the way that I will do that, I'm gonna cross out that column and that row, and I'm gonna do delta y times 0, so I get a 0, minus 0 times this, which also gives me a 0. That means there is no x component on this cross product. And then you will do the same thing in the y hat direction. There is a difference though. For the y, we need to use a minus. So when I take this column and this row out, I get a 0 minus a 0 plus z hat. So I guess I'm gonna do all of the three components. And for z hat, I will have 0 times this, which will give me 0, minus, this is the result, 0 minus delta y times x divided by the square root of x squared plus y squared. So that means the cross product of delta L cross r hat is 0, 0, comma, minus delta y times x divided by the square root. Okay, I do recommend that you become comfortable with a determinant way of finding cross products. It is a very useful process, and you will encounter it often if you are not already familiar with this. So this is the cross product, and now I can go back. And I found 0, 0, minus x times delta y divided by the square root. Now that I have the expression for the cross product, and I have the magnitude, I can use everything in the expression in Biot-Savart's law. So delta B will be the constant. I have the current. I found the cross product to be this result, and then I'm dividing that with the square of this. Now here is what I'm gonna do. I'm gonna take this, since the square of this and the denominator are actually the same, kind of the same thing, I can combine them to write this in a little bit a better form. Minus x delta y, and then I'm gonna take that square root and combine it with that squared, so that will give me parentheses x squared plus y squared, and this will be to the power of 3 over 2. Now I also I do want to write this in a little bit kind of different way. I'm gonna use this, and I'm gonna take the x and the delta y out, and you will see why. And I'm keeping this 3 over 2, and then I'm just gonna write 0, 0, minus 1. So this vector, which is a unit vector, 0, 0, minus 1, is showing me the direction of that short magnetic field, of the small magnetic field created by the short wire. So at the observation location, the fact that everything here is a positive number and this points in the negative z direction with the positive z going out of the board, this means that delta b, okay, delta b is a vector that goes into the board. Now this is the small magnetic field that the short piece of wire here creates at the observation location. What I want though, I want to find the total magnetic field created by the entire current carrying wire. To do that, I need to add all of these contributions to the magnetic field, all of these contributions created by all short pieces of wire. So it's the sum over delta bi and this means I need to add I got the constant. I'm just rewriting this I x. Okay, this will be the delta y and I keep direction. This is the delta y of each small piece, and this is the y of each small piece. Now, the next step, as I mentioned before, once I have the sum that gives me all the contributions from all short pieces of wire, I will make the approximation. I will take the limit where the delta y goes to 0, so that I can think about breaking this current carrying wire into an infinite number of pieces. Okay, that's how you get your analytical expression. So when I do that, the magnetic field from the entire current carrying wire will be the integral. Now I'm integrating, okay, y is my variable of integration. Now because I have placed the 0 here, y will go from minus L over 2 to y equals L over 2, and of course I have the constant. Now the delta y was the length of the short piece of wire when I take the limit with the number of pieces going to infinity. This becomes my dy, okay, the infinitely small length. And then I have I forgot the x times dy, and then I'm dividing this with x squared plus y squared to the power of 3 over 2. Now this is an integral, so this will give you a number. The direction of the magnetic field is given by the 0, 0, minus 1 unit vector. And now x is a constant, okay, right? The position of the observation location depends on x, and I'm keeping that as a constant. I have chosen that from the beginning of the problem. The variable of integration is y, so we can take these things out of the integral, and then you can work out the integral. At the end of the day, the magnetic field from the entire length of the wire, you got the constant, the length of the wire times the conventional current divided by x times the square root of x squared plus L over 2. And this is also squared. So this gives me this expression here. Gives me the magnetic field from a current carrying wire that has a length of L, and it's carrying a current I. X is the distance from the midpoint of the wire to the observation location. Now This is okay. So far, it is important to remember, so far I have not made any approximations regarding, or any assumptions I should say, regarding x or the length of the wire. For any length L and for any x, so long as your observation location is at the midpoint of the rod, you can use this. I forgot the direction, 0, 0, -1. So long as you have the length L and your observation location is at the midpoint of the current carrying wire, you can use this expression. Now, if I will show you in a different video, you can make some assumptions about the length of the rod, the length of the wire, and also the distance from the observation location to simplify this. But this is valid without making any assumptions for L and X.